So we'll do today the standard model finally. The standard model as we know it today. The standard model, the version Weinberg. We have studied the Glashaw's original version without the Higgs mechanism. Today we are going to complete it. We will show how the Higgs mechanism kind of smoothes the rough edges, a few rough edges, and leads to a number of new predictions. But before I do that, what I've done in the last some lectures was to study the nature of the Higgs mechanism, the pattern of symmetry breaking, which we said depended on the Higgs. And we finally concluded that SU2, I can study the breaking by using the doublet version, call it doublet, or I can use what I call the triplet, which is also, if you wish, the adjoint. D will stands for doublet, that we know that. So this is adjoint. Adjoint was a triplet. And we found out this breaks SU2 to nothing through the vacuum expectation value, whereas this breaks it down to U1, which is SO2. It will be useful for us to remember this because we are going to face the choice of the Higgs scalar in a few minutes. So if I want to break all of SU2, I should use the doublet. So here, doublet breaks SU2. And triplet leaves U1. So it depends what I want to do. If I want break of all of SU2, you will tell me, well, use the doublet. It's very easy. And if you are in a situation that you want to leave it, use the triplet. But we call the triplet, we call the adjoint. We thought that the match, remember, just so in other words, a little digression. Here, just once again, reminding you of what we said yesterday, digression, adjoint representation. And how did we define the adjoint? We said sigma goes into U, sigma U dagger. Sigma is Hermitian. Trace sigma is 0. That's an adjoint. It's a matrix. In SUN, this is an n times 10 matrix. U is e to the I theta ATA. A TA is, let's call it here, TA fundamental representation. So in SU2, TAF is sigma A over 2. And we found out, then of course I can write sigma is TA phi A, summation assumed, A is 1 n squared to the minus 1, and in SU2, didn't want it, this is in SU2, I just want, before I do that, I'm sorry, sigma is TA phi A is 1 to n squared minus 1. And put here F, you expand in the fundamental representation. So in SU2, TAF is sigma A over 2. And the phi A field A is 1, 2, 3. is actually transformed as a triplet. We don't have to bug you of SO3, which is the same algebra. Let me ask you, before I go on, I'm about to finish this, because this is not what we will be using in the rest of the course. Which adjoint representation you know? It's always there. Someone wants to try?
The if mu transforms as adjoint.
Size. But even before that, gauge theory is given by covariant derivative. How do you write covariant derivative in any theory? This is an adjoint. Notice you have adjoint means adjoint to the generator. Even gauge bosons, not just F mu. And people often write A mu. You can introduce the matrix called A mu, the red one. This is now an adjoint, precisely. They're real feeds, there are n squared minus 1 of them. And how does it transform? A mu, as you know, transforms. Sorry, you should be in the red. Remember, you actually knew this. There is a plus or minus sign, I believe, a minus sign. Something like this, U, d mu U dagger. Okay, this is the gauge piece. Just don't worry about this. To understand, take theta A is constant. Take the global piece only, and you get that A mu transforms is U, A mu U dagger. You see, this is an adjoint, and it's always there. So it's good that you understand the meaning of adjoint. And then, of course, I agree with you, F mu nu, the same way. If I write F mu nu, as we do, F mu nu A T A, again, you will learn the same thing. This is actually true. This is in general. F mu nu transforms as U, F mu nu U dagger. This is true. The derivative piece, this is true for theta equal theta of x. So these are the adjoint representations. Very good. Is there any last question of this? I want to leave this behind, and I want us to do finally the standard model in its full glory. It took us some time to get here. Lecture number 12. You see, you have to build a formalism. We have to understand the symmetry breaking and some of the associated phenomenonology that you knew but may have forgotten or didn't know. Some of you. Okay. So now we go and study the standard model as a Higgs theory. When you have a theory, you start with a gauge group. I'm speaking about the electroweak part. I forget the strong interactions. I don't work on them the way I forgot gravity. Standard model is SU2L, we said, cross U1 hypercharge. That's the first step. It's fixing the gauge group. We decide. Glesher decided for us. Anyway, not yet, sorry. Then we need what we call the matter. The constituents of matter, which is quarks plus leptons, which the world is built of. And then we said we'll do like this. The maximal parity violation taught us. This Glesher knew. The left-handed guys are doublets. The right-handed guys are singlets. Quarks. ER. These are the particles that can be seen in nature, and this is what I will assume is there. Of course, quarks carry color. We can add it if you like. It's just counting because I won't talk about red, yellow, blue. So this is my matter. Now I defined it. Remember, just this was sufficient to Glesher. From here, we study this. Glesher says, if there is a photon so that it couples to like this, let's write F for fermion. I hope you remember this. Anyway, if not, I'm reminding you. If there is a photon, he doesn't know whether photon is massless. If you tell Glesher that it's massless, he says, okay, it's massless. If you tell him it's massive, I said I will add a mass term, but I will assume that such a particle exists. And then he says, I can prove the following. Now there is a Z boson on top so that it's coupled like this. G over cosine theta W, Z mu, J mu Z, let's call it. J mu A, I could also call J mu electromagnetic J mu A, just to correspond. And J mu Z, I wonder if someone remembers, was F bar, gamma mu, T3. I can put a projector to remind you that only left-handed particles, even if I don't, T3 will project it, minus sine squared theta W, Q electromagnetic. This is what we know, and this is sort of interesting. What we don't know, that we actually predict uniquely the form of the interaction. It's universal, where tangent theta W is G prime over G. U2L has a coupling constant G, U1 has a coupling constant G prime. What else should I say here? Maybe you want to ask me something, maybe you don't. Remember that E is G sine theta W. This is a very important relation. It tells you that E is smaller than G even. Electromagnetic interactions are somewhat weaker than weak. Weak interaction is not weak at all. And we knew, by the way, that was very important. There is a Z boson. There is also a W boson. Do not forget it. Actually, there are two of them. It's charged so that it couples as G over square root of 2 W mu J mu W, which stands for W or weak. Where J mu W is UL bar gamma mu DL. Now I have to be specific. It goes from up and down quark or nu L bar gamma mu DL. 8 equation. So this is W mu plus Hermitian conjugate. And from here we proved that at low energies, the famous G Fermi interaction was G square over 8 MW square, just by exchanging the W boson, which was E square over 8 MW sine theta W square. So what it told us that the theta W is the fundamental parameter. I have to know it. Fundamental electroweak standard model parameter. Weak interactions are weak. This is at low energies. This is at low energies. Electromagnetic interactions would be, so this is weak interaction. This is the famous weak interaction. Why is it weak? Because the electromagnetic interaction would just be proportional to 1 over Q squared. The electromagnetic one. Because photon is massless. So in other words, weak interaction is weak only when Q is much smaller than MW. Then I can speak of weak interactions. Okay, this is the summary of the physics behind the standard model. Notice, however, a fundamental point. People often say that standard model kind of predicts the W mass. I talked about it yesterday and does not predict the Higgs mass. This is nonsense. Okay, even famous people will tell you that this is total nonsense because I cannot predict the W mass. I can predict it only if I know that standard model. So this is my question. Predict W mass, whatever I mean by that. The answer is no. MW was, no, here MW is nothing. I'm before the Higgs. Well, we'll come to the Higgs mechanism in a moment. But one may think that there is a relation because we are saying there is G Fermi. Yes, of course. If there is this Fermi, all that we can say, if you know G Fermi and theta W, then you can fix MW, but that's not a prediction. That's a relationship between the mass and the dynamics. So just remember this. And I will argue that the same is true of the Higgs, that there is no difference. But anyway, this is what Gleshow knew. So now we say, but this is not good enough because the propagator of the Broca theory is not good. We cannot just give these particle masses. We need a Higgs mechanism. Now you know that. So this was the part. I fixed the gauge group. The first part I did. I fixed the matter. And now I need the third. And for us, the central part is the choice of the Higgs. What should I take as a choice? What should I choose? I know. So what do I have to achieve? I have to achieve the following. SU2L cross U1 must be broken to U1 electromagnetic through the vacuum Higgs choice, let me call it phi, through the vacuum expectation value of this phi. What do you suggest to me? Take a doublet or a triplet or whatever? I don't want to take big representation, so I'm asking you, should I take a doublet or a triplet?
Doublet.
Doublet will do the job, precisely. Let's take the doublet. Why? So I want to choose the doublet, thank you. Because I have to break SU2, and doublet breaks SU2. There is even more of a reason. Remember, the way I wrote the matter, and I had no choice, parity violation told me. I could not write the mass term. There is no way I can write the mass term, okay? There is no mass term. Why? Because the mass term would be Q bar Q for any quark, which is called it MQ, which would be QL bar QR. And that is impossible because these particles are completely different from each other. This is not allowed because this is a singlet and QL is a doublet. So what we said instead, however, but we can write a Yukawa interaction, which is of the form, say, QL bar. Let's introduce a notation here for the rest of the course. This we will call QL, and this we will call LL. Lepton doublet, quark doublet. So I will have QL, I will have Yukawa D, phi, dr, for example, I have to write. If I want to give the mass to the down quark, then notice I show immediately here that this must be a doublet. Phi must be a doublet. There is no choice even. It was very easy for Weinberg. Once you get an idea to implement the Higgs mechanism, then everything else followed. Notice that there will be Hermitian conjugate. Let's just look at this term. This will go into QL bar. This is a doublet, U dagger, Yukawa D. 5 would transform as a doublet. So in other words, phi goes into U phi. DR is a singlet, and since Yukawa dagger U dagger U is 1, this is QL bar, Yukawa D phi DR. Very good. It has to be a doublet. This proves it. Checks. What about hypercharge? Hypercharge of phi. How do I decide that? Who wants to help me? Nobody? Remember the fundamental formula? It starts here. Q electromagnetic is T3 plus phi over 2. This was the essence of the standard model of physics. So in other words, I know from here, I know the hypercharge. Hypercharge is 2 Q electromagnetic minus T3. So if you give me electromagnetic charge in T3, and you give me for the quarks, so I find out that Yukawa dr is T3 0, Q electromagnetic is -1/3, so this is -2/3. And Yukawa Q, we found out, I don't want to repeat, it was 1/3. So from here, what do I get for Yukawa phi? Yukawa, sorry, hypercharge, not Yukawa. I shouldn't confuse this Yukawa coupling. My God, it's terrible. We have a similar notation. Oh, but everybody calls it. Now I can see why this notation or Yukawa coupling. This is not a hypercharge. This is just a coupling. You should be able to know from the context. Most people use this as a notation, so I want to stick for that. So tell me, what is the hypercharge of phi? How do I determine? Who wants to help me? I'm stuck. How do I determine the hypercharge of phi? Are you there with me?
Yes, we're there.
So how do we determine it? But look at the interaction. I needed it. I studied it down quarks. Once again, there is a Yukawa interaction. Let's write it again, which is QL bar and dr. And I have to put this phi doublet. And then there is some coupling Yukawa D. Let's make this small. Let's make this smaller. Okay, this should help us not to confuse the hypercharge. Hypercharge is a capital letter. So what is the dr? Is minus 2/3. And QL bar minus 1/3. Look, let's write here the hypercharge. So what is the hypercharge of phi?
It has to be 1.
Right. Sum must be 0. Lagrangian cannot carry hypercharge. What do I mean when I say that the theory is invariant? Means that it's invariant. Means that it's a singlet. Means that it does not transform. You don't want your Lagrangian to carry hypercharge. Charge, anything. Thank you. So hypercharge of phi is +1. That determines everything. Okay, so this was for the down quark. Now I have to write the whole one. Okay, I just need your help. Now we have to concentrate. Okay, we are building it. So now let's do all fermions. So this was down quark. What about the electron? Look, for the electron, it will be like this. It will be LL. It lives in a doublet. Then I will call it some Yukawa E. Then I have ER. Let's check the hypercharge. What is the hypercharge of ER? It's here.
-2.
-2. Thank you. I need your attention. It turns out that the hypercharge of LL is -1. So this is +1. We can check that. We did it. So this is altogether -1. Oh, this is great. I just put the doublet here. +1. It works. The sum is 0. The total is 0. Very good. Now we manage for the electron also. So we check these checks. Electron checks. What is missing is the up quark. We want the up quark to get a mass. It will get a mass through the Yukawa coupling, we notice. So this is QL bar. Yukawa up, UR. And here we have to be concentrated. The QL bar was -1/3. Let me check if that's what I wrote, because I think I did. Yes. So that worked. But what about the hypercharge of UR? What is it?
4/3.
So what should I put here now? Can I put phi?
No, this has to be charged -1.
Yeah, it cannot be. So what should I do? Phi would not work because phi would have +1. And that would be enormous. Lagrangian would be full of hypercharge. I can't do that. So what should I do? What should I do? It won't help me to add a triplet. It won't couple here. After all, I have a singlet, and then I have a doublet. In quantum mechanics, I've been drilling you from the beginning of the course. How do I build the spin zero state in quantum mechanics? I need to, this is a spin zero state. You see, I need a singlet under SU2. So there are two ways. If I have a doublet that transforms as a doublet, so you can think of this upper and lower component, or up and down. Then I have two invariants. D dagger D, that transforms as D dagger, U dagger, UD. This is trivial invariant. What is the other invariant that we talked a lot? What did you use to do in quantum mechanics?
It's D transpose I sigma 2D.
You anti-symmetrize. This is okay, very good, thank you. But the thing is just to remember what you do. I sigma 2 is just in SU2, but you would always, when you build representations of group theory, you always try to anti-symmetrize and symmetrize. That's the first thing to come to your mind. So yes, you anti-symmetrize. So you write this. Well, epsilon is anti-symmetric matrix. So obviously epsilon is proportional to sigma 2. So take I sigma 2. It's up to you. It doesn't have to be I sigma 2. It's just proportional to I sigma 2. So we'll take I sigma 2. We want to be real. I sigma 2 is just a choice. Precisely. Thank you. So I have two possible invariants. Okay, so this was a digression that I can now leave behind. So what should I do here now that you told me what to put here? I have an anti-doublet. All I have to put here is phi star. I take two doublets and anti-symmetrize, or two anti-doublets. This is something that has to get in your blood, in your cells of your body, the group theory of SU2. Exactly the same thing that I did here, because you see QL bar, I sigma 2 phi star is QL dagger. There is some gamma 0, but that's in the other space. That's not in SU2, that's the Lorentz space. So this is QL star transpose, some gamma 0. I don't care about the Lorentz space, phi star. Notice what I did. This is a doublet. Well, I don't have to have the same doublet. I can have two different doublets. Who says that I have to take the same doublet? So here D1 would be QL star, and D2 would be phi star. These are two doublets. Well, the stars of the doublets, not real doublet, it doesn't matter whether I take star or not star, I take the complex conjugate. That's what it is. So we've done it. We've done all the fermions. All we have to remember that if there is phi, there is also phi star. And I had to anti-symmetrize because I have twice the anti-field. Here I have once LL bar, once anti-doublet, once doublet. So here we go. The Yukawa interaction of the standard model is QL bar, Yukawa D, phi dr. Just to have it together, Yukawa up, I sigma 2, phi star, UR. These are the quarks. And then there is LL bar, Yukawa electron, phi ER. There is a Hermitian conjugate. This is very important. That means that I have added the scalar field. Implicitly, we are adding it. That means that I have to add now. So here, add, of course, the phi Lagrangian, which is 1/2 d mu phi dagger, d mu phi minus p of phi. Since it is a doublet, I know the potential. It's good that we studied symmetry breaking. We already did the SU2 part. It's exactly in the SU2. It's of course the same potential because phi dagger phi is invariant under U1 also. So it cannot be simpler than it is. Weinberg was lucky. One doublet suffices. There is a miracle in the standard model. And the miracle is called parity violation. Without parity violation, it would have been a disaster. I try to tell you if the time suffices, but you see the beauty of the standard model relies on the following fact and the simplicity and predictivity, that the right-handed guys are singlets and the left-handed guys are doublets. So with one and the same doublet, I managed to connect all the fermions. This is a remarkable thing. And I show you, we give W and Z will get a mass. Single phi works. This is equivalent to maximal. This is not emphasized enough in the books. Maximal parity violation. I'll come back to this. Anyway, from the potential here, I learned that the vacuum manifold is simply the set of all points. Now this you know in your sleep. This was some funny sphere S3. Who cares? This is just a formal language. I can choose the vacuum to lie on that sphere, and I'm gonna choose this one. I showed you that the choice does not matter. We got the same masses explicitly, but it's just more elegant, simpler, easier to see if I choose this particular version. If I choose a more complicated one, then I have to rewrite the things, redefine my fields. Okay, we can actually try to do that. We can try to play with that. If any of you express a minimal doubt, would like to see that, please ask me. We can think about it. Because you can say, you know, this is Goran, but you are saying phi 0 us. We don't like that. why don't you choose, I don't know, V1, V2? So that V1 square plus V2 square is V square. You could also choose this, you could tell me. So let's forget it for the moment, okay? Let's come back to it. I'm gonna choose because I'm lazy and I like to take always the simplest possible choice. And we come back to this issue. If you have any doubt, okay, please, it's gonna depend on you. It's enough that one of you is sort of curious what will happen. Okay. I'm just using the symmetry factor. You know, you have to write on this particular sphere and all the points on the sphere are identical to each other. Okay, so let's do the, okay, let's go by order. Look what we get. Then let's do first the fermions. Look what happens. I can write, in other words, no, I can do better than that. No, I shouldn't do like this. Let me do like this. From here, I can go to the phi field in the unitary gauge. I will get rid of this unitary. I can get rid of those funny would have been Goldstone bosons that we eat. This is my physical picture. There are no other fields. We show that explicitly. So what do I get? Let's check for the fermions. Look, phi is just the doublet. Notice that you get dl bar. It picks up a lower component, Yukawa d, dr, v plus h. The first term. Phi has a lower component, so it picks up a lower component. In the second term, phi star has a lower component, but sigma 2 flips it. So it picks up an upper component. In the third term, phi has a lower component here. So L picks up a lower component, and that's the electron. So I get EL. I can put here inside. Sometimes I put inside, sometimes outside. It doesn't matter. It's just some coupling. V plus H. There is always V plus H plus Hermitian conjugate. I get a universal form. So I can write from here that for any fermion, now it stands for any fermion, is Yukawa fermion, FL bar, FR. Hermitian conjugate is FR bar FL, V plus H. This is Yukawa fermion, F bar F, V plus H. This is mass of the fermion, F bar F, plus Yukawa fermion, H, F bar F. Yukawa fermion times V is the mass of the fermion, identically. So we got a mass term with Lagrangian. Now it's a beautiful we have a mass term. All our fermions are massive. The theory is realistic. Depending on their Yukawa, they will get an associated mass plus the Higgs coupled to, as I promised, to the fermion mass. This is the standard model Yukawa interaction. Cannot be simpler. All that mass of doublets and so on disappeared, and we just have massive. Just have the mass term. Higgs interaction. Celebrated Higgs interaction proportional to the mass. This is very important. The mass is now a dynamical parameter. If you know the mass, you know the interaction, okay? You can probe the Higgs mechanism. Very good. We have to go on, we have to do the gauge fields and so on and so forth, but it could also be good time. Why don't we make a break so that you can pause, you can think about it. Please check these last few formulas, see if everything was clear. And I suggest we come back at noon in 6 minutes, please. We are back. Any questions, please? Again, this should be sort of familiar. This is what we found in the U1 case. Remember exactly the same situation. The Higgs was coupling to the fermion mass. This is a very important generic feature in a theory where the symmetry allows for a simple Higgs. So in order to complete the symmetry breaking, in order to understand what is physically going on, in order to interpret this well V, after all, what is this V? We have to look at the gauge boson masses. And interactions. So let's keep this. Let's keep our phi to be phi unitary, the physical gauge, which is 0V plus H. And then 1/2. No, let's write first. It will be maybe more useful if I just write what the covariant derivative is. So d mu 5 then. It is d mu h, of course. That's just the covariant. That's just the derivative of h that will give me kinetic energy. I can forget about that. Minus Ig. And then Ta, oops. It's a doublet. Minus, maybe I should write this more neatly. I'm sorry. That's a very important formula. So there is a doublet 0 d mu h. But I'm really not interested. I'm interested in this. So let me just write, it will start like this. 5. This will give me the kinetic energy for H. So I'm going to drop it. What I'm interested in is the gauge boson masses and interactions. So I will just go into this term, minus E 1/2 A mu A sigma A times phi. So let's be explicit. This is minus I G over 2. Then sigma 1 and sigma 2 are off diagonal. So I will get the upper component. And that will look like A mu 1 minus I A mu 2. Agree? From sigma 1 and sigma 2, are you checking on me, please? Sigma 3 has a diagonal form, so there will be a minus sign, A mu 3 times V plus H. Correct? In other words, d mu phi is 0 d mu h minus Ig over 2. Let's write the complete formula. A mu 1 minus I A mu 2 minus A mu 3 V plus H. So 1/2 d mu phi dagger d mu phi has a kinetic energy. There will be 1/2 d mu h squared that you expected, and maybe some interaction of d mu h with other guys. What is crucial here, I will get plus this second term. This is our term. Since I'm taking the absolute value square, I will have 1/2 G over 2 square. Oops, I made a serious mistake. Nobody corrected me. My God. What a disaster. What did I forget? Need your help. I'm gonna write like this. What did I forget, please? Someone should remember. What is my gauge theory? SU2 or
The part of U1.
U1? U1. Covariant derivative is not what I wrote. Something is missing. Let's make a little more space. I wish I could say I did this on purpose to see if you're following me. Minus IGTA A mu A times phi minus IG prime, the coupling constant. The generator is called Y over 2. That's our convention. The gauge field is called B mu. And we have phi. G prime is the coupling constant over U1. I hope I've written. Yes, I did. Generators. The gauge group with the generators TA for SU2 and Y over 2 for U1. Okay. I goofed. So there is a B mu piece. So here, in other words, there is G prime B mu. It's just a number because Y is 1. I'm using that Y acting on phi is just 1. So I can forget about, I took a half out. I was almost right, but the mistake was dramatic, although it's almost. So this shouldn't be G here. It's minus I over 2. G is here. And then minus G A mu 3 plus G prime B mu. So I get A mu 1 square plus A mu 2 square. I write this separately just to emphasize the point, plus 1/2. I'm going to write like this, G square plus G prime square, and then minus G A mu 3 plus G prime B, and I will divide because I multiply by G square plus G prime square, everything square. Does everybody agree with me? This is what we are after. Something is missing, V plus H square. Okay. Do we agree on this? Did I get it right finally? Or I goofed again? I wonder. I think I got it right now. So tell me, what is the first piece? A mu1 plus a mu2 squared. You remember what it is? We discussed it before. When we check the interactions with the fermions. We introduced the particle, you remember this? Called W boson, A1 minus plus I, A2 over square root of 2. Why? Because this is the guy that interacts with up and down. Then I have, okay, everybody remembers this, please? Tell me yes or tell me no, or you want some comment here.
Yes, very well.
This is studied at Lex. I'll remind you again when it comes to it, okay? But I will leave it aside now, okay? This is a W boson because really what happens, okay, it is this guy that couples with the interaction G over square root of 2 U bar gamma mu D. For any upper and lower component, okay? We can also write here immediately that there is an, well, no, we'll write it later. No, maybe we'll write immediately. We get the following interaction, 1/2 mw squared. No, let's leave it. What we will have from here, we write the interaction later, that mw, there is a factor G over 2 times V. We saw it in the SU2 case. This is not different. The W boson when we did SU2, of course, is the same W boson in the SU2 theory. The fact that I have U1 doesn't affect the W boson. And the mass comes from this V term. This produces a mass term. We'll talk about the Higgs interaction later. What we need here is the mass term. This is crucial. W is A1 and A2 components, and they have a mass. There is a half term, proper normalization, G over 2 times V. Now notice the following thing. You see what I've done? I've divided by G squared plus G prime squared so that I have a normalization. Notice that I have two states. A mu 3 and B are neutral states. Neutral gauge states, gauge boson states. They are not particles. They are not physical states. They are just initial fields. They are not eigenstates, not eigenstates. Or mass matrix. Not eigenstates or mass, so they cannot be physical. Notice, I don't have A3 squared plus G prime. I have a linear combination. Notice from here immediately that there is one linear combination orthogonal to this one. There is a combination G, A, no, sorry, G prime, A mu 3 plus G, B mu. Okay, I can do better than that. Out of these, I can do better than that. I have two combinations. One is minus G A mu 3 plus G prime B mu over square root of G squared plus G prime squared. It has a mass. Notice that it has a mass term. So let me call it, let me give it a name. I'm gonna call it Z. And I have that mz square is there is a half in this, so it's 1/4 V square G square plus G prime square. It's here. Notice I have an extra term. No, not G prime square over 4. Because I've taken, I've divided and multiplied. There was 1/4 coming from the here. The same that we had for W mass. This guy is massive. There is another linear combination that I called G prime, must be orthogonal. Let me call it A mu. With MA is 0. I've written in big to give it a thought of big importance. I don't have to do anything. These are already normalized states. This state is massive. Out of 2 states, 3 and B, 1 linear combination, properly normalized is massive. Notice that this field that I called A is massless. If you look back what we did in one of the lectures, this is precisely the photon. It couples. We already found it. Let's assume that there is a photon. We prove that there is a photon. In the standard model, photon is absolutely massless. The question of photon mass does not arise. This is a prediction. Since tangent theta W is G prime over G, you can write now that photon is sine theta W A mu 3 plus cosine theta W A mu. This is the celebrated photon. The Z boson is orthogonal. Minus cosine theta W. Overall sign is irrelevant. You can take, some people take with that, because it will go as a m square plus sine theta W. No, this is not A mu, please. Are you, don't let me make these mistakes, please. This is B mu. I started with the fields A mu 3 and B mu and got 2 orthogonal combinations with an important predictions. This is with an important prediction. There is more to it. MA 0. And MZ is predicted not by itself, but as a ratio of W mass. W mass has G squared, this has G prime G squared, MZ is MW over cosine theta W.
Sorry, Prof.
Let me just write here, please. MW is G over 2V. And I simply use that cosine theta W. Let me just remind you, it's G prime. No, it's G. And then you will ask me a question, please. G over square root of G squared plus G prime squared. This is why I have this prediction. Yes, please.
I want to confirm something. For the expression for that Z mu, what if I write it as cos theta W A mu 3 minus sin theta W B mu?
It's the same field. it's defined up to a sign. This often happens that the fields, the sign of the fields are not physical. You know, the fermion even is defined up to a phase. When you write the field, it's up to you. And Y you see here is defined here. I have a square here. So obviously what I called as a particle, you see what's going to happen here? Also, there is an additional thing that we have to show, that this photon field, but we already studied it, couples like this. So suppose I write like this, V mu, J mu Z, where we wrote J mu Z. But you're saying, what if I change the sign? So you have Z mu, you know, let's call it Z mu Goran. I don't know how to make sure. Since it was up to the sign, you are saying, but there is a sign question. Okay. But notice when I change the Z boson, I will have two vertices. So there is a sign question here. So there is a sign here. There will be plus or minus here, according to what I'm saying. But there will be also plus or minus here. So plus or minus times plus or minus is plus. There is no ambiguity. It will take care of itself. And sometimes our ambiguity will be much bigger when I write down. Look, just to remind you for fermions, I write M fermion. This you have to remember, F bar F. You're saying, oh, what do you mean by F? So this is, let's call it F Goran. But then you say F us is some e to the alpha F Goran. And you get that F Goran bar, F Goran is F us bar, F us is the same thing. There is an ambiguity. There is a convention in defining the fermion field. You have to remember that this is extremely important, because sometimes you will think, oh, there is some phase in the game. I'm gonna now introduce a phase because I write F us as e to the I alpha F Goran and I have an extra phase. No, that phase will disappear. This is particularly important when we discuss CP violation, okay? So here, this was defined up to the sign, okay? It was a sign choice. The physical quantities, the scattering amplitudes, the mass term, notice that the mass does not depend on the sign choice because you get mz squared. Just to remind you that Procca field is minus a quarter F mu nu plus 1/2 MA squared M mu A mu. F mu nu is d mu A nu minus d nu A mu. Notice that there is a mass and sign choice. Sign ambiguity. It goes as a square. I don't care whether you call it A mu or minus A mu. We are talking about the same physics. Because nothing depends on that sign, as we can see explicitly here. Okay. What else do I want to say here? I don't know. I have to pause. I have to see whether you want to ask me questions. Okay, notice that we have a fundamental difference. So in the glacial theory, Glacial has a SU2 cross U1 gauge model. He built it first. He doesn't have the Higgs mechanism. Therefore, he says, if there is a photon, then there is a Z boson. He says, I don't know what the photon mass is. I don't know what the Z boson mass is. To be precise, I don't even know, says Gleshow, what is mz over mw. No, not zero. I wanted to write a question mark, I'm sorry. By this, really, I mean the following, that mz over mw is a question mark, not predicted. Even the photon is not predicted. The only thing is, if there is a photon with that interaction, I get the Z boson. So there is a beautiful connection. Z boson with its precise J mu Z, that was fixed. And A boson with its precise J mu A, that he has to assume, Gleshow, okay. Whereas there is a Weinberg version now, what we studied Weinberg, which is a Higgs version, the same gauge group as you do cross U1. But because of the Higgs mechanism as a completion of the theory, you predict there is a photon. It's not if, there is A so that MA is 0. And that linear combination actually, and it couples as A mu, J mu electromagnetic. I may remind you, but we derived that. There is also a Z boson. So that MZ, this is beautiful, over M, so that, let's write like this, so that MW is MZ cosine theta W. And there is also, and you have G over cosine theta W. You have everything is predicted. Z mu, J mu Z. So what is new? Photon is massless. Charge is conserved. And W and Z mass correlated. This is new. Remember, the standard model does not predict theta W. Theta W you get from experiment. And you find out, you don't predict, I'm sorry, that it's almost 30 degrees. If you remember 30 degrees, that's good enough for me. More precise number is 0.23. This is very important. That once you measure the theta W, now I can do everything. I can predict MW is 80 GeV. Remember, there is a formula from here. Since I know the Fermi interaction, it was E squared, which I know. I can actually write more clearly for you, 4 pi alpha. Electromagnetic, that's E squared over 8 MW squared sine squared theta W. From here, you measure G Fermi. So you get this very important. Standard model predicts the W mass, predicts once again from the interaction, relates it to the interaction. And then the second thing you get, MZ immediately you predict is 90 GeV. Because you know theta W. You put the number here in this relation between Z and W mass, and you get 90 GeV. This is a great success of the standard model Higgs theory. Agreement with experiment. Okay, perfect agreement with experiment. Even when you do the loops, people have done loops to compute these masses. This was 3 level. There is now high precision. Okay, as the time goes on, standard model simply becomes more and more successful. Perfect agreement with experiment. This was new. Let me now finish. I wanted to say more, but I won't, not at the end. I'm more or less there. Why there is a massless photon? We can ask, how come we got a massless photon? Why did we predict it? Well, remember how the symmetry breaking goes? We have a phi doublet. And I chosen this. You can choose any other. You will see the same thing. Notice that TA acting on phi 0 is non-zero. These are Pauli matrices. SU2 is broken. This means this is equivalent to say that SU2 charges, all three of them are broken. Also hypercharge acting on phi 0. Since this is equal to phi 0, this is of course not 0. It's 1. So this is equivalent to saying that U1 hypercharge is broken. But notice, please, Q electromagnetic, remember, is T3 plus Y over 2. So look at this here, Q electromagnetic acting on phi 0 is minus a half, no, plus a half, 0, 0, minus a half. This is T3. Y is 1. So it's 1/2, 1, 0, 0, 1, acting on phi 0. I'm being very pedagogical. You could see this immediately. This is 1, 0, 0, 0, acting on 0V. This is 0. It's true that we break SU2, and it's true that we break U1 hypercharge. But Q electromagnetic acting on phi 0 is 0. Charge, and by this I mean electromagnetic charge, is not broke. Of course, if the charge is not broken, remember, if you don't break a symmetry in some direction, you will have a massless gauge boson. Or better to say, the reason you get a massive gauge boson, because you broke the symmetry. But we didn't break all of the symmetry. We broke all of the SU2. We broke U1, but the linear combination remained. Now, I have a question for you. This is a question you should ask me, but I have a question for you. I still have a few minutes. That's because we took phi 0 Goran is 0V. But now you are saying, why don't we take a different one, which is V0? Now it seems, look at the Q electromagnetic now is in upper direction, acting on phi 0, us is 1, 0, 0, 0, V0, apparently, which is non-zero. So what is going on? Is Goran stupid? Are we stupid? What's going on? Now, Q electromagnetic is broken.
I think we have to take different linear combination for this.
Yeah,
case.
of course. Of course. It's obvious. This is not Q electromagnetic. This is wrong. That's what Goran chose for Q electromagnetic with his conventions. The conventions are chosen so that they fit you. So in other words, this was really, when I say, if I say that phi 0 Goran is 0V, that's like saying that Q electromagnetic Goran is T3 plus Y over 2. By the way, where Y of phi is equal to phi, that's also convention. It was all conventions that we have, we can revisit them. But when you say that phi 0 us is V0, then you will see that Q electromagnetic us or U, it's not us. It can be, for example, T3 minus Y over 2 with the same convention. Or you can even take Y over 2, but you change the convention for the phi field, which means that you change the connection for the electron. Everything has to be consistent with everything else, of course. And my hypercharge was consistent with the charge of the electron plus 1. So here, it's very easy to see that this one, for example, acting on phi 0 us is 0. There is always one linear combination which is unbroken, obviously. You will just put different coefficients. You see, you have one wave, only one wave, one field, one wave, and you have two neutral generators. One linear combination can always be unbroken. Please try to think about it more. And think if you ask me, because you can now say, okay, but why don't we take phi 0 devil's advocate? I don't even want to take like this. I will take V1, V2. What about now? What happens now? Well, there will be some, for sure, Q electromagnetic devil, so that it acts on phi 0 devil is 0, but you have to find it. It may be more complicated. Prove. Think about it. I'm ahead of myself, so I can stop here in peace. Yesterday I needed a little more time. Today I can finish ahead of me. I give you back those, I don't know how much, maybe not 10 minutes, 5 minutes. So you want to ask me something? Or you're all hungry?